To determine if a population is evolving, we need to be able to measure changes in allele frequencies in a population. So let's imagine we have a population of dot bugs, and blue is the dominant phenotype for these creatures, and red is a recessive phenotype. And in this population, we have 4 animals that are red and 12 animals that are blue. When we look at this population, we know that the animals that have the recessive phenotype have the homozygous recessive genotype. But out of the blue animals, which ones or how many are homozygous dominant and how many are homozygous recessive? In the entire population, all of the dominant alleles plus all of the recessive alleles equal all of the alleles in the population. So for the first Hardy-Weinberg equation, P equals the dominant alleles and Q equals the recessive alleles. But since some of the animals have a dominant phenotype, we don't know out of those animals how many are homozygous dominant and how many are homozygous recessive. The second Hardy-Weinberg equation is going to help us determine out of the ones that have a dominant phenotype, how many are homozygous dominant and how many are homozygous recessive. In this equation, P squared represents the homozygous dominant animals, 2PQ represents the heterozygous animals, and Q squared equals the percent of homozygous recessive individuals in the population. Since we know how many animals have the recessive phenotype, we also know what percent of the population has the homozygous recessive genotype. It's 4 out of 16, or 25% of the population. That means that Q squared equals 0.25, or 25%, and we can use that to solve for the other variables in this equation to figure out what percent of the population is homozygous dominant versus heterozygous. The first thing we need to do is get Q by itself, so we're going to take the square root of both sides of the equation. When we do that, we get that Q equals 0.5. Now be careful with this. When you take the square root of 0.25, it's not 0.05, it's 0.5. So make sure you get your decimal in the right spot. Now that we know that Q equals 0.5, we can put Q into that first equation, P plus Q equals 1. If P plus Q equals 1 and Q equals 0.5, then we can get P by itself equals 0.5. Now that we have the values for both P and Q, we can plug them both into the second equation. So P squared equals 0.25. 2 times P times Q equals 0.5, and Q squared, as we already had, equals 0.25. And when we add them all up, it equals 1, for 100% of the population is either homozygous dominant or heterozygous or homozygous recessive. These values are exactly what we would get if we started with a population of heterozygous animals and we did a Punnett square, but it also works for other values. This time we're starting with a population of 100 animals where 36% of the population has the red phenotype and 64% of the population has the blue phenotype. You might see a question like this on the exam that gives you this information and then asks, how many animals in this population would you expect to be heterozygous? Remember, the 36% of the population that has the recessive phenotype is also equal to Q squared, which represents the percent of the population that is homozygous recessive. The 64% is less useful. It's P squared plus 2PQ. Since there's 2 variables that are unknown in that part of the equation, we can't use that. So we should start with Q squared, which is the percent of the population that has the homozygous recessive genotype and the recessive phenotype. Remember, Q is squared, so the next thing that we have to do is get Q by itself. So to start these problems, remember that the percent of the population that has a recessive phenotype equals Q squared. And the first thing we have to do is get Q by itself. In other words, take the square root of both sides of the equation. When we take the square root of both sides of the equation, we get Q by itself equals 0.6. Now we can take that 0.6 and put it back into the first equation, p plus q equals 1. So if q equals 0.6, then p equals 0.4. Now we have the values for both P and Q. Q equals 0.6 and P equals 0.4, and we can put those back into the second equation, and that will tell us what percent of the population is homozygous dominant and what percent of the population is heterozygous. When we put these values in for P and Q, the equation tells us that we expect 16% of the population to be homozygous dominant, 48% of the population to be heterozygous, and 36% of the population to be homozygous recessive. And you can always check your work with these problems because when you add these components up, it should equal 1, or 100% of the population is either homozygous dominant or heterozygous or homozygous recessive. The values for P and Q tell us out of this entire population how many of the alleles are dominant alleles and how many alleles are recessive alleles, regardless of whether they are in one individual or two individuals. So let's think about what that means. Individuals that are homozygous dominant will contribute 2 copies of the dominant allele and no copies of the recessive allele. Heterozygotes will contribute 1 dominant and 1 recessive allele, and homozygous recessive individuals will contribute no dominant alleles and 2 recessive alleles to the population. In this population, there were 16 individuals that were homozygous dominant, so 32 dominant alleles came from those individuals. There were 48 individuals that were heterozygous, so 48 dominant alleles and 48 recessive alleles came from those individuals. And there were 36 individuals that were homozygous recessive, so there were 72 copies of the recessive allele from those individuals. And when you add up those totals, it equals the number of alleles in the population and shows you where we get the values for P and Q. You can test your understanding of these problems by giving yourself your own made-up problems. The easiest ones are ones where Q squared is a perfect square. So try this problem, where 81% of the population has the dominant phenotype and 9% of the population has a recessive phenotype. Go ahead and calculate how many Hardy-Weinberg would expect to be homozygous dominant, how many to be heterozygous, and how many dominant alleles or recessive alleles you would expect to see in this population. The purpose of using these Hardy-Weinberg population equations is to determine whether there are changes in the value of P and Q. If there are changes in the values of P and Q, it could be either the conditions for Hardy-Weinberg equilibrium are not met, or evolution is happening through natural selection. But the only change in allele frequencies that lead to adaptations is natural selection.